This is the final device for the counting circuit. It has been taken into a custom 3D printed PCB case, and the PCB is laying inside of it with the battery inside. It's down and up. And in the next couple of minutes, I will break down each process of this circuit and tell you how they work and how this circuit is able to count. This is the initial button input to the circuit. It is a PBNO in a pull-up resistor configuration with a 10K resistor on it. So this means at rest a high is given to the output, and when pressed a low is given. This allows the circuit to start the counting process. This is the NAND gate oscillator, arguably the most important part of the circuit. The NAND gate oscillator generates a clock signal and for the circuit, essentially acting as the heartbeat. It works by connecting NAND gates with capacitors and resistors to create a feedback loop. This feedback loop revolves around the discharge and charging of capacitors through resistors. The first timing network is made up of resistor R2 and capacitor C1. These control how quickly the voltage at the NAND gate rises and falls. When given power, C1 begins to charge through R2, and while charging, the voltage at the next NAND gate input slowly increases. This circuit combines digital and analog components using voltage thresholds. It converts the analog signals coming from the capacitor and resistors into a digital output using NAND gates. Capacitors C2, little one here, and these two resistors make up the second timing network. This makes a delay and forces the NAND gate to toggle between states instead of just settling on one. The values of the R4 and C2, the capacitor and resistor, determine the oscillation frequency. Increasing them will slow it down, and decreasing them will speed it up. The NAND gate is in my opinion, the most important part of this circuit. This is the 4017 decade counter. The decade counter generates a different output for each rise or falling edge that occurs from the clock signal. The clock signal is taken right from the NAND gate oscillator. The 4017 has a different output 0 through 9 on one of the 0 through 9 pins for each of the digits. Seen in this video, it is progressing 0 through 9, and that last red LED is the divide by 10 pin. The divide by 10 pin takes the frequency of the clock signal and divides it by 10. This is very useful for a circuit to slow down the counting frequency. Next is the 4510 chip. The 4510 allows the circuit to count numbers up or down for the counting circuit. The chip does not count in decimal numbers, however. It counts using binary. The chip has 4 separate outputs, each of which represents a bit in a 4-digit binary number. This can be shown using the LEDs in the picture. When the clock signal is inputted, each of these 4 LEDs will turn a certain color, allowing it to form a 4-digit binary number. The chip has an up and down pin, which allows the circuit to count either up or down. A slide switch can be used to interchange between the two with ease, as pictured here. The 4511 chip, or the BCD decoder, receives the 4 signals from the 4510 chip and turns that binary number into a decimal output using the 7-segment display. Inside the chip, there is logic gates to know what segments of the 7-segment display to turn on to display the correct number. For example, when 0010 is sent to the 4511, it decodes the input and activates the correct segments of the 7-segment display to display the number 2. To do this, you must connect each lettered output of the 4511 to the correct lettered input of the 7-segment. This allows the chip to receive the binary input and decode it into a decimal output. The 7-segment is lettered very similarly to the outputs of the 4511, making wiring straightforward. You just got to connect the lettered outputs of the 4511 to the inputs of the 7 segment, and this works. The 7 segment plays a crucial role in the output of this circuit as it digitally displays the numbers being counted. In this circuit is a CA, or a CC, a common cathode 7 segment, which means that all of the LED's cathodes are connected, and these common pins lead to ground. This is effective when working with chips. This is the final completed version of the counting circuit with my personal extension, which is the ripple counter. The ripple counter uses AND and NOR chips to count up to 9, and then when that 9 counts back down to 0, and then back up to 9. This cycle repeats the entire time. This can be done using AND and NOR chips, as well as a 1-bit memory circuit known as an SR latch. An SR latch is a type of flip-flop which is required to connect to the 4510 up or down pin, so it remembers the last signal it was given. This allows for the circuit to count seamlessly and automatically change direction when needed.